إيه أتوقع الكل راح إيه إن شاء الله. دكتورك موجود؟ هم دكتورك راح يكون موجود إن شاء
لا
الله.
شكله مو موجود، ولا دكتور أورليان.
لا يحضرون حبة حبة. الحين وقت امتحانات الكل مشغول. الكل مشغول يسوي الامتحان. يعني إذا عنده مواد مو موحدة، اللي عنده مواد موحدة زين، اللي جام يعني مو واحد بس يسوي.
نعم صحيح دكتورة.
Hi, hello everyone.
هاي دكتور.
hello.
Hi, hello.
How are you doing, doctor?
Everything is going well. Thank you so much. How are you, Muhammad? Are you ready?
Yeah, hopefully I am. I hope so, yeah.
Okay.
We read your project report. It's lovely. You've done a great job.
Thank you so much, doctor.
Yes, it's really a good job. Yeah. I took a look and it's really great. Congratulations.
Thank you. Highly appreciate it, doctor. Thank you so much.
It is nice training for master degree. Very nice training. Yeah, you just have to keep it bigger a little bit.
Bigger a little bit? Inshallah. Inshallah next time, inshallah.
Okay.
For the master.
And you will have, لا for master. I mean for master degree. Yeah. But for now it is lovely. بعدين تخرع الطلبة. ما نبي نخرعهم.
Maybe I don't want my master in control theory. Allahu alam.
Yeah, it's okay, but you know at least how to think about the project and how to write it and what is the sections. The math you will have a lot nowadays of application in math. Also in the department, many professors are open to many projects, applications.
Right, doctor, yeah.
Everyone, I just wanted to show some appreciation for Muhammad and the math department for allowing me to teach Muhammad and Eid. You have the best students, honestly.
Thank you so much, doctor. Thank you so much.
أهلا دكتور. كني شلونك دكتور يحيى؟
الله بخير. أنا دكتور. How are you doing?
الله يسلمك. كني شايفتك في لقاء تنويري.
عدل شايف لقاء تنويري. مر عندكم القسم أكثر من مرة حاضر حق محمد couple of talks.
لا يبينا نسوي جروب تعارف. Good relation between engineer. أنا الحين حاليا نسعى يعني لأن ما شاء الله عندنا فرصة وايد حق a nice research together. Yeah.
Definitely,
many great ideas.
And you have very much very bright students, honestly. Like right now, I taught two of them in my classical mechanics class. Muhammad was about to take special relativity with me, but it had conflicted with his schedule. But lovely students, honestly. MashaAllah, good job. Math department.
الحمد لله.
السلام عليكم دكتور.
عليكم السلام. كيف حالك؟
الحمد لله رب العالمين. كيف حال دكتور؟
الحمد لله. جاهز خلاص؟
الله يسر دكتور.
إن شاء الله.
إن شاء الله.
minutes to go. أهلين دكتور يعطيك العافية.
الله يعافيك. حياك الله.
It's a great job. You done a great job with Muhammad.
Thank you. He did a great job, yeah.
Yeah.
I like it because there is a lot of from the functional analysis theory, and it's really a nice job.
Yes.
Yeah, I wanted to apply, like we want to do a merger of pure and applied mathematics. Yeah. I received a comment from. Please, doctor.
Yeah, go ahead. No, it's okay.
I just want to say that I received a comment from Dr. Milicha. She said, "Oh, you are into applied math, not a pure math. You seem like a pure math guy." I said, "Oh, it's all right, doctor. There is
no difference between applied and pure now."
Yeah, that's right, doctor.
No big difference. No difference. Almost the same. I hate when they said pure or applied. We can do the both. We need the both.
That's right. Before we start, if you don't mind, we are having a trailer for the presentation. It's a video made by one of our friends. He's currently here, Muhammad, yeah. It won't take that much time, so don't worry about time being time-wise. Yeah. We have taken everything into consideration.
Okay, now I will allow you to present, so you can share your screen, and we can start for 1 minute. Okay, if you're ready.
Yeah, definitely.
Of course.
Definitely. Shouldn't we wait for Dr. Aurelian, or that's fine?
Yes, let's wait.
He's
Yes,
there.
of course.
He's there.
Yes.
Aurelian is with us.
Oh, hello everyone.
Yeah.
Hello,
Nice
doctor.
to meet
Welcome,
everyone.
doctor.
Yeah, I'm here. Thank you.
Thank you.
So ready.
Hi, hello.
Hello,
Thank
Ariel.
you. Hello, doctors. Nice to see you.
Oh,
Hello, doctor.
okay.
This is a good occasion to meet again.
Lovely.
Even from
yeah.
Yes.
even online.
You
It's
have
not
a
too bad.
hard job this semester. We have
Indeed.
a lot of good seminars from our student.
Indeed.
Okay.
Thank you.
Okay. Let me introduce you, Muhammad. Today we have an honor to have Muhammad in his project, Muhammad Bastaki, with the Professor Boumediene. It's a great honor at Kuwait University to have this project done. It's an old dream for me, and it's come true now. I was a dream when I was a student at Kuwait University that as other department we can have a project course, but they refuse. So to my knowledge, I think this is the first project course, and Muhammad Bastaki will be the first student to take an honor course realistic, because at Kuwait University we have a graduate with honor grade, and it's depend on doing a project, but they keep it up to the grade. If the student have GB 3.75, he will have graduate excellent with honor. But graduate excellent with honor must be with a project. So Muhammad and Professor Boumediene make this dream come true. It's a great honor to have you, Muhammad, today. Everybody know you as a hardworking, a great student who give a great talks. I have an honor to teach Muhammad, and I can thank you, Professor Boumediene, for taking Muhammad in this course. I know it was a big effort from you. You never you give him all the best attention and improvement he need. Thank you so much, Dr. Boumediene, for taking this course, and I hope all other professors and doctor can have some student in this project. Muhammad, you can start your great talk today. Welcome everybody. Hope to enjoy this talk. Thank you.
Before I start, I'd like to thank Dr. Mariam for her great introduction, and also I'd like to thank her for her permission to allow us taking this course. And I hope that the rest of the math majors will also be taking it hopefully soon. So before I start, we have a tiny introduction, a tiny trailer to.
Yes, Muhammad, you can share your screen.
It seems that there is a technical problem.
Yes, it's a mute.
Yes.
شو صار؟
He's frozen now. Okay. Maybe he will be back soon. Good. Muhammad, I admit you.
Hello?
Yes,
Sorry.
Muhammad.
Okay, sorry. So I had trouble with my connection. Is my voice now clear?
Yes.
Yes.
Okay. Okay, so let's start, inshallah. Okay. Okay, so before we start, actually, we have a tiny introduction. This introduction was made by my friend, and don't worry about time because it is being put into time-wise. So please, let us take some time into seeing this. Okay, where did it go? Okay. Okay.
ننسى الأيام الصعبة وبالمحبة اللي بنشرحنا والدنيا بتضحك لما بنضحك بتزين أفراحنا ورد وبحر ونارنجي أرحنا الأسامي زينة الحارة فرجي الياسمين الشامي الندل بيزرع فني يحصد شر الندالي والعز بيرجع للي عنده حكمة وأصالة واللي بيحلف يمين كاذب يا ويله من الله واللي بيحلف يمين كاذب يا ويله من الله 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 الله.
Okay, so thank you so much for listening to the introduction. So now, inshallah, we shall start. Before I start, I'd like to thank my supervisor, Professor Boumediene Chentouf, for his great devotion for this work and for his great support, and also for the committee members and for Dr. Maryam Al-Kendari for her great support. Okay, so first of all, we start with an overview of our project. So before we start, we define what a partial differential equation is. So a partial differential equation is simply an equation that involves finding a function, a multivariable function that depends on a number of variables, and also that equation contains the rates of change of in different directions. There are many types of PDEs, and in this part we shall take consideration of two different PDEs that are the reaction diffusion equation and secondly the wave equation. The main aim of partial differential equation is at modeling numerous physical phenomena, and we'll see how is that related to today's talk. So again, as I've said earlier, that is the main prompt behind finding a partial differential equation comes from mathematical modeling. So there is a question that has arisen alongside the question of modeling systems. Can the humankind take an active rather than a passive approach to partial differential equations? That means, can we influence those partial differential equations? Can we influence the dynamics of a partial differential equations? Can I change the behavior of the dynamical system I'm studying, the modeling system that I'm currently investigating? And the answer is yes. And due to that, we have a fascinating field that has emerged, which is called control theory. And the idea behind control theory is that humans take an active approach to studying PDEs or any other systems. And our aim would be then to stabilize that system, guide it, regulate it, or observe it, or even stabilize it. However, the aim behind this project is to discuss the problem of stabilizing the equations. And today we'll discuss the problem of stabilizing of reaction diffusion equation, and secondly, the wave equation. Okay, and before we start, we have some functional analysis preliminaries, and that's due to the fact that the solution of OPDE, they lie in infinite dimensional spaces. So this requires basic tools from functional analysis. So those tools from functional analysis enable us with dealing with the problems of existence, uniqueness of solutions. And throughout our journey, we will discover and discuss an important class of operators, which are called semigroups, as well as very interesting spaces, unorthodox and revolutionary spaces actually, which are called Sobolev spaces. So Sobolev spaces, those are the spaces in which it allows for functions that are not differentiable in the classical sense to have some notion of differentiability. So from here we shall start and discuss the preliminaries. Okay, before we dive into the definition of Sobolev space, we define the notion of a test function, because we will be using the notion of test function in order to define the notion of a weak derivative. That is the extended notion of differentiation. So let's assume that we are currently dealing on an open interval in the real line, that is a to b. So we define phi, that is a continuous function, that interval. We define its support to be the closure of the set of values in I, such that the phi does not vanish over it. And then we define the test functions, and it is the set of smooth differentiable functions where that got compact support. So that support is going to be compact and also is going to be compact in I. So these functions are denoted as test functions. From here, we define the notion of Sobolev spaces. So we say Sobolev space consists of the set of all LP functions through which we can find G that belongs to LP, such that this equation is being satisfied, and this is being tested against the set of all test functions that are in there. And that G that we have seen over here is that weak derivative. It is that extended notion of differentiability. And interestingly, if we have a differentiable function, that G is also going to that weak derivative is going to coincide with the normal derivative or the classical derivative that we already know from our previous courses. And when P is equal to 2, we denote a special case, that is, we denote it by H1. Okay, and the norm of W1P is going to be equipped with that norm, and this is going to be the inner product. Okay, so that definition was just made for the sake of knowing the first weak derivative. That is kind of the first derivative of my function. So if I want to proceed on, we could generalize the Sobolev space to contain also the weak derivatives for nth order or m order. So we define the WMP set to be the set of all that's defined by U that belong to LP, and the set of the weak derivatives until we reach to the M1. And this is going to be the norm of the WMP space. And when P is equal to 2, we have this special case. And also, since we'll be dealing with partial differential equations in which we have boundary conditions, homogeneous boundary conditions in which they vanish, we define W01P. W01P, mathematically, it's being defined as the closure of the set of differentiable functions on I with compact support. So that means I can approximate any function by a continuous function with compact support in W1P. Okay, so we can characterize that function. We can characterize a function belonging to W01P as a function that vanishes on the boundary of that open interval. And in this case, it's going to be the endpoints of my open interval. And we can also have it generalized for the m derivatives, such that means we have the weak derivatives until m-1 is going to vanish on that boundary. We have also some inequalities that will be useful later on in our proofs. Hilbert's inequality, Young's inequality, and Poincaré inequality. Okay, and as I've mentioned earlier, we will be dealing with the notion of a semigroup. Okay, so the idea behind semigroup is that it extends the notion of e raised to the power of at. So if A was fine dimensional matrix, interestingly, I can write that as the infinite summation of atn over n factorial. However, there are many cases in which A might be unbounded. So using EAT would not make any sense after that. So we have to generalize the idea behind EAT. And luckily, we have the tool to do so. So we have the extension of that what's called semigroup, which is called a semigroup. So if we have a Hilbert space, we define that family of bound linear operators to be strongly continuous semigroup if it satisfies these properties. T at time 0 is equal to I, t plus s is going to be t of t times t of s. And also this condition will imply the strong continuous part. Okay? And also we have important definition that we say an operator is going to be an infinitesimal generator of C0 semigroup. That means I can generate that C0 semigroup. And it is defined by defining, first of all, its domain. That is the set of all the elements that belong to my Hilbert space where the limit as t approaches 0 t of t x minus x over t exists. And a of x is also defined that way by taking the derivative of t of t x at time equals 0 from the positive side. So in order to discuss whether a semigroup is being generated by an operator or not, we have to check these three conditions. That is, A shall be linear with dense domain, and S should also be dissipative, and there should exist also lambda in which the range is going to be H. So yeah, and it generates C0 semigroup of contraction. That means the norm of my semigroup is going to be less or equal to 1. And interestingly, semigroup is going to provide a powerful framework for analyzing partial differential equations by transforming them into some sort of an ordinary differential equation, which is called an abstract Cauchy problem. So my aim over here is to find that Q with that initial condition X that belongs to my Hilbert space that we had earlier. So abstract Cauchy problem, we'll see that name come a lot over here. So we have two types of solutions to that abstract Cauchy problem. The first being a strong solution. So a strong solution is simply a solution that is, first of all, that is going to be also continuous and also differentiable. However, we could know if an abstract Cauchy problem would admit a strong solution if my initial value belonged to that domain of that operator which is acting on U. That is the A over here. Okay, so if A is going to be an infinitesimal generator, therefore we have a unique strong solution. And we also have the notion of a weak solution, and we say that a function is going to be weak solution of the abstract Cauchy problem, which is this one. If I can find a sequence xn that belong to my domain such that xn goes to that initial value, and ttxn is going to converge to ut uniformly on those bounded intervals. We have a very useful result over here. That's if I have an infinitesimal generator of a C0 semigroup T of T, that satisfies this inequality. And if I have a bounded linear operator, A plus B is going to be the infinitesimal generator of a C0 semigroup, and it would satisfy that one. Okay, so yeah. So afterwards, after we defined what an abstract Cauchy problem is and semigroup, we can discuss the stability, which is the main cornerstone behind our definitions over here. So if I have an abstract Cauchy problem, after transforming a PDE into this abstract Cauchy problem, we can discuss its stability. So we say the equilibrium point of my system is stable if for all epsilon greater than 0 there exists a delta such that the norm E naught, that is my initial solution, is less than delta. Therefore, my time trajectory of solution is going to be less than epsilon. We say it is also exponentially stable if the time trajectory of my solution is of exponential order. It decays at that order. And we say it's unstable if it is not stable. You simply take the negation of that. 250, no worries. Okay, so after we're done with preliminaries, we can discuss our first case, which is being the reaction diffusion equation. So what are the reaction diffusion equation? Reaction diffusion equation actually is a powerful partial differential equation in which many physical phenomena is being modeled after that. So in reaction diffusion equation, we have two terms, as the name suggests: a diffusion term, reaction term. A diffusion term is that term in which a quantity is being spreading through the space, while the reaction term is the local reaction in that either amplifies or dissipates that quantity. And for the sake of simplicity, we're just going to consider a one-dimensional heat equation case, the evolution of temperature on a thin rod given different situations. So first of all, we have this system of partial differential equation. We have a partial differential equation, an initial boundary value problem. Here we have Dirichlet homogeneous boundary conditions. So that means I have a thin rod, and the temperatures at the endpoint of the rod is at 0. Okay, so here we have that term, which is going to be the diffusion term, and that term is going to be the reaction term. Using semigroup theory, I can show that problem is well posed in the set in the L2 0 to pi space. Okay, and by using semigroup theory, we can say, given that U naught also belongs to the domain of A, I can show the existence of a strong solution over here. Okay, if I assume currently that A is constant, by using the separator variables like what you took in your PDE class, I can express that solution as a Fourier sine series, and the coefficients are going to be given in that way. Okay, so if I just take care of that exponent of that part A minus eta n squared, I can find three cases in which, first of all, the zero solution is exponentially stable, the second being stable, and the last part unstable. So we say that if A is less than eta, that the zero solution exponentially stable, that means the rod is cooling down. That if you have any initial temperature, is going to decay rapidly to zero. If I have stable, okay, you might be wondering, what's the difference between stability and exponential stability? Exponential stability would guarantee that the temperature is going to rapidly decay to zero given any initial temperature. While the zero solution is going to tell me that the temperature is going to be remaining bounded, and it would settle into a steady profile. However, it does not mean it would necessarily vanish. While if A was greater than eta, then that means that the rod is going to be overheated. That's the case when the zero solution is unstable. So that was the first part when A is constant. And if A was going to be a function of X, we consider the energy. And in order to discuss the stability again of my solution that is related to U, since the energy is defined in terms of U, so discussing the stability by using that definition would correspond to discussing the stability of the energy. And by integrating the energy and applying Poincaré inequality and using bound of A, because we are on a compact interval, so it would attain the maximum, we would get this beautiful inequality. So we are over here, we have the energy, so we get different results. That if this part was greater than if we have the norm of A, it is less than eta over Cp, that means the energy exponentially decreases. While if a norm of A was equal to eta over Cp, that's the energy is non-increasing. It's going to be remaining bounded. While if the norm of A was greater than eta over Cp, it may increase and could cause instability, which would lead to overheating. Okay, so now we consider another problem. In which here we have mixed boundary conditions. We have a Newman condition, that's ux pi of t is going to be 0, and the initial date is going to satisfy this case. So again, we can show the problem is well posed by using the semigroup theory, and a unique solution exists. So we don't have to worry after that. So again, by applying the same methodology as before, if A was constant, we just discuss the solution by discussing it from the exponent. We get also the same three results. We have exponential stability, stability, and instability. And again, if A was a function of X, by recalling the energies defined that way, we get also the same results as before: exponential stability, stability, and instability. So now, after we discuss the stability of the previous problem and discuss the three cases, now I want to actually stabilize it. Now I want humankind to take an active approach on it. I want to stabilize it. I want my rod to cool down. I don't want it, let's say, for some A to let's say to overheat or temperature is bounded. I want it to cool down. So over here we introduce a method which is called the backstepping method. So the idea behind backstepping is that I transform my possible unstable, or perhaps it could be stable but not exponentially stable system, into a target system that is exponentially stable. And we do that by having an integral transformation, and afterwards we obtain the control. So we add a new term into my equation, either interiorly or in the boundary, as we will see shortly, that's going to affect the dynamics of my system and make it exponentially stable. So here we have a boundary input control. So back then we had this phi to be 0, but right now we have phi to be a boundary control input. So right now my goal is to design that control such that the system is being exponentially stabilized. As we have seen earlier, that A became unstable when it was sufficiently large and positive. So we transformed that system into this system. And interestingly, by using this theorem, by using the tools of function analysis, we can see that the system that we intend to go to is exponentially stable. So these functions are a very good candidate. So now my aim is to find a suitable integral transformation. And we introduce a full integral transformation to B. In that case, where we go from the U state into the W state. However, my aim over here is to find the kernel. And we obtain the kernel by substituting that equation into a PDE system. We obtain afterwards a kernel which is going to satisfy that system. However, and also since we are doing the following adjustments, we can also obtain the boundary feedback control. Since the intended system we wanted to vanish at the boundaries, and that's 0, so my feedback control shall satisfy that equation. So this is a candidate for my feedback control. So before we go on, we shall prove the theorem that the kernel that satisfies this equation exists and is also unique. And we do that by introducing chain of variables, a defined function of g in terms of eta and psi. And by substituting into back, we obtain this PDE system. By integrating the first equation twice, we obtain the following integral equation. So my aim now is to show that integral equation has a solution and it's also unique. And we do that by using a method of successive approximation. So we define a sequence, that is my G0, and this is my iterative sequence, Gn in terms of Gn minus 1. So by using the upper bounds, we can see that Gn is bounded above by those. And this is the definition of M. So we introduce the following series G that is being taken as the infinite summation of my Gm. And we shall see by the Weierstrass M test, using this part also, that the series is uniformly convergent. And this will be very helpful because we have this G as a candidate solution. So we substitute that G into my integral equation, and using the idea of if uniform convergent that you can switch between the infinite summation and integration, we can see that it's a solution to the integral equation. So now we have shown the existence of the solution. So now I want to prove the uniqueness of G. So we consider the following homogeneous equation, which is done by subtracting G1 minus G2. We assume like we have two equations, then we make them equal. And by applying upper bounds and taking them onto small intervals, I can show that the only G that is going to satisfy this equation is whenever G is equal to 0. Lastly, I want to show that if I transform from U to W, I can go back from W to U. And this is done by showing that this map, that is the K, admits a bounded linear inverse. And this would also give us some useful inequalities later, as we will see hopefully shortly. So after the theorem is being proven using the tools of function analysis, we can prove that this closed loop system, what I say about closed loop system is that we have that original system with that control that's being put onto the boundary. This is called a closed loop. So I want to prove it is exponentially stable. And by applying the inequality, since I already know that the target system is exponentially stable, and we know the fact that K, that is the transformation, was bounded and also invertible, we can clearly see from the last part that now we have shown that the original system with that feedback control has become exponentially stable. Okay, so now I consider another case in which we have ux1 of t, that's my von Neumann condition. Rather from it having 0, I also impose the binary control, and also by transforming it into a target system, which is that one, which is exponentially stable. We also define an integral transformation. We also, throughout our work, we also find the boundary control as well, by plugging into there. And since we know the integral transformation, we can also deduce by the same procedure as we did before that the closed loop system with that control, that is the original system with that control, is indeed exponentially stable. So now we are done from the first part about reaction diffusion equation. Now we move on towards the second part, which is discussing the wave equation. So let's see what we have about wave equation. The thing is that in stabilizing the wave equation, we use a different procedure. That is the energy method. So here we have a one-dimensional wave equation, which you have probably seen in your PDE classes or in your physics classes. U here represents this vertical displacement of the string from its equilibrium configuration, and C represents the speed of wave propagation along the string. So we discuss now the problem of stabilization of the wave energy. But you might be wondering, isn't it already stable? Let's see. The thing is that if let's consider the following system. This is my wave equation, and we have homogeneous by the Dirichlet boundary condition, that is displacement at the endpoints is vanishing. So we define the energy of system to be this one, which is also related to the norms, and the definition also comes from the law of physics. However, for the sake of simplicity, we are mathematicians, so we take the work of physicists and then apply it to our work. we can clearly see that if we take the derivative of E with respect to time, it is going to be 0. That means the energy of system is conserved. Okay, but you might be wondering, Muhammad, why are we doing this? The thing is that over here, if I have a string, if I bring it over here and then oscillate it, it will keep oscillating until time until time that's going to infinity. However, I want my string. So I want my string, let's say the amplitude, I want it to decrease time by time. I want it to decay. I want my string, let's say, to calm down and then become a vertical one. So yeah, this was the problem. It is indeed stable. The equilibrium state was indeed stable. However, it is not exponentially stable. So what do we do over here is that we apply a control. However, the control now is added onto the boundary. That is the interior control. And we also have the energy defined by the previous way. So how do I find a good candidate for the interior control? Well, simply, I will take the derivative of energy. We will just have that part that's being left by applying integration by parts and also boundary conditions. And since I want the derivative of energy with respect to time to be less or equal to 0, we choose the candidate feedback control to be minus KUT. This would be really good. And if we substitute into back, we'll see the energy is not increasing. That means it functions as a very good candidate. So now my goal is to show that using this phi, that is the feedback control that I introduced over here, and that system is going to be exponentially stable. My ROP is going to decay. The amplitude is going to decay, and we just have a flat one. So first of all, we will show that the previous equation, it admits a solution is also unique. And this is done usually in your PDE class, for sure in your PDE class. So using the method of separator variables, we obtain that one. And by evaluating 33 at t equals 0, which is obtained also from their boundary conditions, we obtain u0 and u1. By using the orthogonality, we find an and bm. And substituting the u back into my equation, we get an ODE that will determine to me the coefficients, which are the C and T. We obtain a characteristic equation and obtain the values for omega n and for m. And depending on the variable of my and depending on the sign of my omega n, whether it was positive, negative, or 0, we'll have different. We will have kind of different solutions. And I think this will be a good exercise for those who are taking differential equation right now. Okay, so we obtain the following. Result, and those are gonna be my coefficients. So it varies whenever omega n is different. However, now if I want to discuss the feedback, if I want to discuss exponential stability, so we assume that we have a k that will satisfy this inequality. So now I want to show the closed loop system that is the system that I had initially, plus with the boundary control is going to be exponentially stable, where the decay rate is going to be given by that one. What's the decay rate? So basically the key idea behind the decay rate is that if the decay rate was maximum, I can be sure that my rope is going to, let's say, is going to become horizontally faster. That's the basic idea behind the decay rate. So again, how do we prove this? We first of all we define the initial we had defined the initial energy, which is defined this one. We have u1 u0 prime. We obtain it from the previous equals we have, and by also deriving the estimates for the coefficients that will be useful in finding the ET. By also using Young's inequality, Poincaré inequality, and by using tedious algebraic work, we have E of t. And then by estimating E of t with my E0, I can see that the energy has become exponentially stable now. So that means my closed loop system now with that feedback control has become exponentially stable. So now we shall discuss the feedback, the decay rate. So we consider this function that is obtained from the decay rate. We see that the maximum of that function is achieved at that one. So that means that is the k in which the decay rate is happening the most. So by designing that control, since I am free to choose my k in my control, I choose my k to be that one in order to have my solution decaying as fast as I want, as fast as possible. Yeah, it's gonna be the maximum one. Okay, so now we consider another problem. However, in this problem, the thing is that we have mixed boundary conditions in which we have a Newman condition. So what it tells me right here is that the display is not changing. The thing is that the rope is going just to be horizontal on one side. However, on the other side is going to be fixed. So let's assume that we don't have that velocity feedback, which is the control. If it was equal to 0, by using again the same methodology as before, we see the energy is constant. However, now by introducing this feedback control, by again using the same procedure as before, we will obtain the following results. So my goal now is to show that this that this closed loop system with that velocity feedback is going to be also exponentially stable. So this is going to be my energy functional. So what we are going to do, or the method in order to prove that it is exponentially stable, we define a perturbed energy. It's something that would be much more easier. So the perturbed energy is defined to be that one, which depends on epsilon, as we can see. And we are going to show that using this perturbed energy, that the energy that I had earlier is exponentially stable. So first of all, we do it first of all by showing the equivalence of the energy with the perturbed one, by doing tedious algebraic work, and by using Poincaré, Young inequalities. And secondly, by differentiating by differentiating the perturbed energy, we obtain this equation. By applying to this algebraic work, integration by part, Young, Poincaré, we obtain this inequality. And by choosing suitable delta and omega, which I'm free to control, I'll make sure that this part is going to be negative. And by choosing the minimum, I can obtain this alpha. And then by using the equivalence, I can get this equation. And since, again, the perturbed energy is equivalent to my energy, we could see that the energy has become exponentially stable. Okay, so that was for this case. So now let's assume that rather than the control acting on the interior of my domain, it is acting on the boundary. So we have here the energy. Again, it is defined in this way. So my aim is to design a boundary control by, again, taking the derivative of E, since I want it to be decreasing. So this would function as a very good candidate. Okay, so again, my aim is to show that the closed loop system with that phi is going to be exponentially stable. By, again, defining the perturbed energy, showing its equivalence, we secondly show that it is exponentially stable. And then this sigma would be of our interest because it represents the decay rate. Okay, so first of all, since we proved the equivalence, secondly, again, we differentiate phi of t by applying the necessary formula for E sigma and also E prime. We obtain the following one by choosing delta such that it is negative. We obtain this following equation, and by using energy equivalence, we obtain also the value of sigma explicitly. So over here, we can deduce the exponential decay of my energy, where you can go from here to here by using the energy equivalence. So here we could see that the energy has become exponentially stable. And by discussing the maximal decay rate, pardon me. So again, since the sigma over here, it depends on delta, and since delta after here, we could choose it. We choose its upper bound from here. We can obtain this formula, and if I maximize the delta, then my sigma is going to be maximized for small delta. So we clearly see by doing the algebra that if k is going to attain its maximum at k is equal to c. So this is going to be my optimal choice in which the maximal decay rate is going to be yielded. So from here, we finally reached to the conclusion of this talk. So first of all, we developed functional analytic framework. So this was based on Sobolev spaces. We discussed infinite dimensional PDE, and also we have applied semigroup theory to discuss the Cauchy problems. We also ensured that this is the unique solution, which was a core thing in our discussion today. And also we discussed the control of reaction diffusion equation by applying the backstepping method, and we applied it with different boundary conditions, whether they were mixed, Dirichlet, Newman, and also the controls were applied interiorly and the boundary. And the same discussion was done for the 1D wave equation. And these are the references. So at last, I'd like to thank everyone who has attended today's talk, and I hope that you have enjoyed today's talk. So any questions? Thank you so much again.
Thank you so much, Muhammad, for this great talk. Bless you. It was a great effort from you and your professor, Dr. Boumediene. Thank you so much. You have a great attendance, Muhammad. The number of attendance is 48. This is a great number. Any question, please, Phil? Please.
Hello, Muhammad. Thank you for
hello, Doctor.
your
How are you doing,
invitation.
Thank you so much.
I'm all right. I can't be more proud. This was a very well done presentation, very well articulated. Great effort there as usual. Yeah. Thank you for your invitation.
Thank you so much. Dr. Noor has taught me English 162, so it's a pleasure having her again. The thing is that
yes,
back
from
then
a
when
language,
yeah.
Go
please,
ahead.
Doctor, go ahead. Yeah. Yeah, because back then her comments was that I used to take a lot of time. I used to take excessive time in my presentations. But hopefully today, I hope that I managed well with my time.
Watching you grow like that in Kuwait University is really very, very wonderful and makes me very proud. Well
Highly
done.
appreciated,
Continue
Doctor.
all your
Thank you
hard
for
work,
your
Muhammad. Thank
you so much, Doctor. Pleasure having you.
Yeah.
Okay, so so we start with questions. Please, Dr. Kyriakos.
Congratulations, first of all, dearest Mohammed, and congratulations to your supervisor, Professor
Thank you so much.
Boumediene. It was really, I was confused. I thought it is a master thesis presentation. Or
Not
even
yet,
PhD
Doctor.
thesis. It's a very, very high level, and I would like to tell you that I feel really emotional. I mean, I don't think that there are European universities which can offer this kind of thesis in this level. Congratulations. Secondly,
thank you so much, Doctor.
I would like to
appreciate
challenge you. I would
yes,
like
Doctor.
to challenge you.
No,
I would like you to tell me if stochastics or fuzzy is a better approach to control theory. I will challenge you. Think about it. Maybe you can think in the future. Is it stochastics or fuzzy logic? Because you attended the seminars in fuzzy logic, and you realized that we believe that fuzzy contains probability theory, which is the diagonal, you know. So,
yeah.
Do you have any answers right now or not?
Currently, I have nothing in my mind, if I were honest with you. But hopefully, I'll be thinking about it. Hopefully, yeah. Any approach to stochastic. I think that perhaps it will be better for modeling, let's say, complicated systems, because for right now we have, let's say, simple systems like one-dimensional cases, and the examples, let's say, were taken to be the simplest, just for the sake of simplification and illustration for the audience. But yeah, I believe definitely it would be a better approach, definitely. But I think that would be much more suitable for, let's say, more complicated physical phenomena. That's what I really think about it. I hope that I've given an answer for you, Doctor.
Definitely, this is also for the future, a discussion for the future. Thank you very much.
Definitely, Doctor. Thank you so much, Doctor.
Congratulations.
Bless you, Muhammad. We might take you in fuzzy. We don't have special
Doctor, I want topology.
You can do, Dr. Kyriakos have topological research with fuzzy. Bless you.
Thank you so much,
Muhammad. Dr. Dragon, Professor
yes,
Dragon, you can proceed.
Professor, yes. If you want,
I would like to congratulations.
Okay.
Oh, sorry.
Thank you so much. Do you want me to
I would like to
congratulations
to both, to Muhammad and the supervisor. So you gave both the great effort.
Thank you so much.
So this is my first time that I see the part from the functional analysis, and I was really happy to see, that someone is also interested in this part. So all the best in your future works. Yeah, thank you so much.
It was great having you here. Thank you so much, Doctor. Please, please, Professor Najib. Yeah.
Thank you, Muhammad, and congratulations you and your supervisor for this nice work.
Highly appreciate it, Doctor.
My only comments, which is I think for the future, you handle nonlinear partial differential equation. The case study that you took is the linear PDEs. So
that's
maybe
right,
for the future you handle the nonlinear case. But excellent work for an undergraduate student, and this is an excellent work. Okay.
Highly appreciate, Doctor. For sure, we'll be dealing with nonlinearity, like what we did in our case and dynamical systems course. Thank you so much, yes. Doctor. It was very
congratulations
beneficial
again.
for today's Doctor. Highly appreciated, Doctor. Thank you so much. Please, Muayyad.
Yeah. Thanks a lot for the talk. It was very well structured.
So much. Highly appreciate that.
Do you think you have sort of a physical meaning as to why you choose the perturbed energy to have that form? Like you choose it to have a form of epsilon, the integral of u times ut.
Okay, so I think the form was, let's say it was useful because let's say after further investigation, you want your E of t to be equivalent to your E epsilon t, to your perturbed energy. So that form would be, let's say, of usefulness because also it will be later on improving exponential stability. So I think it's done, let's say, by further investigation because this work was taken from the references that we have used earlier. So yeah, I think this work would take, let's say, pretty much some time in order to obtain that equation, and I think that was no way doable in this short period, let's say, of a few months.
Yeah, I would assume that there's a sort of physical interpretation, like if you have Hamiltonian, you observe the sort of the variation of the wave.
Yeah.
You look at like a perturbation in that. I think you might also get the same form if you look at the Hamiltonian of the wave. I'm not completely sure. Maybe I'm completely wrong on that.
Yeah,
but
definitely.
If there was a physical interpretation, that would be nice. I will look into it and tell you if there is.
Yeah, definitely. But I think that this talk, let's say, is devoted to being way mathematical. That's why.
Yeah, I understand.
Even though that I presented some physical, some intuition from physics. That's why. Thank you so much again for your question.
Of course.
Dr. Kyriakis, again, you have any question? Okay, I think he left this.
I'm sorry, I forgot to raise it down. Sorry.
Okay, thank you, doctor. Does anybody else have any questions?
Okay, great, Muhammad.
Please, doctor.
Great.
Okay, thanks.
Sorry.
Dr. Khalifa. Please, Dr. Khalifa.
Yeah, please, Dr. Khalifa. Oh, I thought nobody.
Abdurrahman. Okay, please, Dr. Khalifa.
Salam, everyone. First of all, congratulations for this excellent presentation and excellent project.
Thank you so much.
Okay.
Yes.
I think you focus. I think these projects focus only on for some applications on wave equation. What happens, for example, for the case of Laplace, for example, or and also, and I have a question about when the domain of X is infinite, okay, is not finite.
The domain of X, currently we are dealing with infinite dimensional spaces.
Because we suppose that the domain of X is finite, okay, is okay. For example, when,
yes. Okay, shall I open the slides again? Yeah, I think that would be better.
The space variable. He means the space variable X is infinite.
Right now we do.
Yeah, from zero, let's say you have infinite or semi-infinite string for
what happens?
I think because for now we were focusing, let's say, on physical applications, like what made intuitive for us right now. That was like our motivation right now, but we haven't actually delved into the cases when it was infinite. That's the thing.
It is doable. All these things can
doable,
be done. Yeah, all these things, even from nonlinear, semi-infinite, infinite, all these things are the fuzzy control. There is a fuzzy control. All the questions raised, we have answers, but it's beyond the the level.
Bachelor, beyond the
and
level.
Even the question raised by Maid. There is a physical meaning of the perturbation. It is definitely there is, yes.
Okay, thank you so much, doctor. What was again your question, doctor? Have you? I think you asked another thing also.
Yes, for Laplace equation, it's stability for the case of Laplace equation.
No, we haven't either even dealt with the Laplace equation right now. We just took those cases and discussed them in depth. That's why. But for sure it will be doable, as also my supervisor, Professor Boumediene, has said also.
And I have also a question. Is there any other approach, for example, because here you use semi-group approach. Is there any other approach to study the stability of these PDEs?
For studying the stability, because the semi-group theory over here, we mainly use it for proving the well-posedness of the problems. But regarding the stability, we actually employed other methods that are feedback control, the backstepping method and the energy method.
Okay.
I hope that was your question, doctor. Yeah.
No, that's okay. Because
okay.
Okay. Thank you.
Okay, Doctor. It's fine, Doctor. Yusuf, please, if you got any question, yeah.
Assalamu alaikum. Actually, I don't have a question. I just like to thank you for your effort today, Muhammad. I would like to thank all professors who attend with us today. It's such a pretty beautiful day. Actually, I'm from other college. I'm from business college, but I made sure to attend today because I believe that I will gain benefit academically from your talk today. Whatever your name is, Muhammad, creativity is there, skillfulness is there. And I know you're from primary school. We all together were from مرحلة الأولى ابتدائية. I don't know how to describe in English, but بالعربي we say يعني شطارة. أنت متفوق وشاطر ويعني you have a potential, a great potential, Muhammad. So I wish you all the best. And it's like a dream day today. So thank you so much.
Thank you so much for attending, Yusuf. It was a pleasure. Really wishing you also all the best with your studies. Allah يوفقك يا رب. Any other questions? Or let's say like any other further questions that perhaps will also
or any
Muhammad,
or any other comment if the student want to ask about the project, the procedure, anything, and about any comments for Muhammad presentation, please give a comment if you don't have a question.
That's fine. Comment.
So
I think currently there are no comments. Yeah. Perhaps there
no
will be
comments. They will say to you many comments. Hello?
Yes,
you done a great job, Muhammad.
Thank you so much.
And thank you everybody for attendance. You give a great honor to Muhammad by attending his talk. Many all the friends, many of your doctors and many different departments. That's great, Muhammad. Thank you, Dr. Boumediene. I have
Dr. Okay. Please, Doctor. Yeah.
So please, this should encourage all professor in mathematics department to have some student in a project course. I really encourage you to take student with excellent grade. We can do a great job with them, introducing them to the research. Yes, please.
Actually, Doctor, I think it would be better, let's say, like having interdisciplinary work, like working with a supervisor from here.
Yeah, sure. Yeah, it is lovely. And you know, this hard work from Dr. Boumediene is not count in his work, but it is a good effort he introduced to the department. And I also encourage the students, all math students with great grade, more than 3 point something, they can ask some professor, or we will have an open day so you can know who the professor is willing to do some research with you in this course. It is a 3-credit course, and you will love the work. It's something different from ordinary course. It's not depend on the exam, but it's need hard work. At last, Muhammad, I want you to give the student some notes about how this course work, compare it to the ordinary course with exam. Please,
definitely,
Muhammad.
Doctor. But before that, I think we either have a comment or a question from Muhammad Al-Ainiya.
Thank you, Muhammad. Actually, I don't have a question, and I'm even from a different college, but I just want to say I'm so proud of you, and you encourage us as a student to do this masterpiece of research. Thank you so much.
Thank you so much. Currently, Muhammad he got a team. He and his team are working on building a submarine right now. It's because he's a computer engineering student. So yeah, also alhamdulillah, yani, we are graduating right now. Alhamdulillah, ala kulli hal. Okay, so as Dr. Mariam said, let's say what comments that I currently have about the coursework. The thing is that the project course is very different. It actually prepares you for graduate work. And the thing is that, like, while applying for graduate schools, which I started from this year because I had hope of going into graduate school abroad, many actually ask, like, what project have you done? And so on. So I think, yeah, taking this course would actually prompt them to accept you as students, yeah, because it will be actually because it will be actually done in discipline right now. Like, you have a supervisor, it's also verified by the department. So yeah, I actually really encourage everyone to take it. And also, I'd like to thank the chairman, Dr. Mariam, for her great support into making this dream actually come true. Hopefully, inshallah, we will also see this course becoming mandatory also in the next few years. And also, I'd like to deliver my thanks for Professor Boumediene Chentouf. I hope I was a good student. Because I was actually always keeping procrastinating, even like I spent many weeks, like, let's say, being busy with something else, and he actually, let's say, prompted me into working again, especially like with the events that we had earlier and the sirens that are coming in and out. But hopefully, but gladly we have made this dream actually come true. So again, thank you so much, Professor Boumediene Chentouf. Thank you so much for your great support, for your great guidance.
You're welcome.
I actually learned a lot from this course. Learned function analysis, both of that. Like, I learned the entirety of crisis. Then actually never see them again in completing my project. But it actually, let's say, connected the gaps of my understanding in the world of function analysis. And also, I hope to have function analysis being offered, because I've been waiting, me, also Muayyad, we have been waiting for many years for function analysis to be offered. Inshallah, we can see it having been offered. And at last, I'd like to thank everyone over here for your attendance, for your support.
Sorry to interrupt you.
Yeah,
Can you discuss to the student what is the hardest part in this course?
Hardest part of this course is that, like, you have to rely more on yourself. Like, you don't like, there are no lectures. There are no lecture notes, so you have to rely more on yourself. You have to read the references. You have to understand things by yourself, and like asking your supervisor. Yeah, I think that I can say this is, let's say, the hardest part of this course. Yeah, yeah. Maybe I have advices, but this will be for later on, because currently I have nothing in my mind.
Yeah, can I ask now, Dr. Boumediene? Thank you so much, Professor. Can you describe this course for us as a professor? Do you encourage us, and what sort of a student can we have in this course? And what sort of a student we have to avoid for this course? Please, Dr. Boumediene.
Oh, thank you. That's a difficult question to answer, but usually if you give a project, you can design the project according to the student. That's okay. If you have a good student like Muhammad, who can read and then try to understand things, so you can raise the level of the content of the project, like we did. This is actually the beginning of graduate level courses, like functional analysis, infinite dimensional systems, and things like this. So it depends on the students. If you have a good student, you can give a good, very good project like this one. I mean, as a level. If you have a medium student, you can also give you design a project where you introduce students to simple things and try to guide him or guide her. So it depends on the students. So this is, but according to my knowledge, the university regulations are there. I mean, the GPA should be very high. This is my understanding, to get a project, right? I think this is the rule. So we are a little bit, I mean, in terms of choices, limited. So we need to have good students according to university regulations. But usually I was in other universities like Oman, where any student should take a project at the end of the year. It's a must.
Yeah, I think, Doctor, this is the rule. It was meant to be in Kuwait. Yani you can graduate good with honor, but I prefer that at this time we started with an excellent student. Then we will have after sometimes, because sometimes a student can be very good or good, and they are good in research and they love to read and to discover some things by their own. But I prefer now for next year we started more with all the excellent students.
Yeah, definitely. For good students, you can do it. I mean, it's very doable. I mean, we design a project in a nice way, and then we guide the students throughout the semester, and it should be okay. I mean, but as Muhammad said, the difficult part is to rely on himself or herself. Yeah, we need, that's the point. I mean, of course, as I said, the students will be guided by the supervisor. Whenever there is a